thanks everyone for inviting me, and I'm excited to talk a bit about how we approach standardization in Roche. And I on purpose depict or use the title, which is a bit of pushing in perhaps a different direction, and really asking in the Monty Python way, what has standardization ever done for us? But let me elaborate on that during the talk a bit more. So let's start with the Lab of the Future, and I'm actually grateful that I'm the first speaker here after Daniel showed the recent developments of SiLA, and in SiLA in version 2, which I'm pretty sure will bring us closer to that vision that is depicted here. And this is indeed a quote, that the Lab of the Future, and I skip most of the words here, is a place where the scientists really can get straight to the process of experimentation. Well, now you can think, I have here now the nice drawing, which looks more like an assembling line, perhaps, in the automotive industry, where I have a lot of high throughput devices and all of that. And thanks to Tom, actually, who always takes those nice pictures of, similar labs actually at Roche. So we have things like that as well, where you have really, even conveyor belts, robotic arms, and all of that. And the question now is really, is that of the future? Is that really a place where the scientists can get to the process of experimentation? And I would, really question that, because let's look at, a bit of the history of life science research. Typically you started, a lot in the biologics labs, I would say, but the chemistry lab, it's not the pipette, but it might be a bowl or something like that. But typically you had a very human-centric, I would not call it automation, but workflow. So for example, with traditional pipetting, you had one human, one sample, one pipette to transfer a sample. Smart people already scaled that and said, like, hey, I can scale it with a multi-head pipette and already, gain something. And exactly where this is going. Now, if I take a robotic device, I can go onto, the order of magnitude of 100, roughly, for those sample transfers. And well, yes, then we can even scale that one, and then we are at that factory. Then we are here where we kind of scale automation. Yes, that is kind of nice, but at what cost? And the cost is, of course, that I have to deal suddenly with things like error handling, data storage, tracking, inventory. I need a lot of systems around my actual, sample transfer to support such an endeavor. Now, the point is, if I look from left to right, how flexible is left, how flexible is right? On the right-hand side, is it really that I can just go there and do experimentation? That seems to be like a mismatch here. Meaning, to reach the right-hand side, probably standardization will help us. If you want to stick to the left side more, well, we need a bit more of flexibility. And so the question is also in that life science research automation space, as I would call it, how much automation is really needed, but also how much standardization is kind of needed. And just to show you a concrete example, we at Roche a couple of years ago started to see, like, okay, hey, automation becomes more and more important, and not only what I call physical automation, so robots, machinery, and all of that, but also data automation, meaning automating data flows, and that includes from devices to any kind of IT systems. And as you can see here, to come closer to that, factory picture, but perhaps not really at that factory picture or that assembly line picture, you have to do a lot of transfer of data between devices and any kind of instrument, any kind of systems, like an ELN, but also inventory, registry, and all of that. And that became for sure a bottleneck, because at one point the scientist could scale, her or his throughput on, sample transfer, for example, with a liquid handler, but not really scaling also the data transfer. Yeah, so we said, okay, hey, what can we do there? And I talked about that solution, which we term AutoLab, in plenty of conferences, and you can even find videos about it. So in essence, it's basically a BPM engine that drives the digital workflow forward and automates certain data tasks, transfer of data between instruments and devices, but also data wrangling and data processing and all of that. And while we, of course, implemented, that solution and now, even scale that up, of course, the question comes, okay, what about that instrument integration piece? And indeed, if I just show you here a bit of the software architecture, and I don't want to go into detail, what you clearly see is, I'm talking here at the SiLA conference, why is SiLA not there? And to be honest, when we started that project roughly 3 years ago, we had hundreds of instruments, or on the order of 100 instruments in scope. And we checked, okay, how many are kind of SiLA compliant? We found out that those are 2, and they were at the bottom of our prioritization list. And actually, they were even SiLA 1 adapters kind of available, and not, SiLA 2. And so we really said, okay, hey, is that really the right way to go? But what we decided then was finally, hey, we do simple file transfer, very, very simply. And that was done with a message queue. Does that now mean, for us, SiLA 2 is not really, the answer? And I would say no, because what we clearly see now also in the future is the following. In the life science R&D, it's not like you build it once and it's like an assembly line and it will run for 10 years or 5 years or 20 years, but things like this can happen. So you flip out a certain instrument, a certain component to something else. And that, is kind of needed on the one hand to be flexible in your R&D workflow, but also that should not take too long. And there I would have hoped that, a standard like SiLA 2 would be implemented, because that would make our life way easier to implement such a thing. Because, and that's, the great question, even now, after only 3 years, such workflows undergo changes already. And that can also be because, an instrument is kind of flipped out. Yeah. And so, you really come to the question, and I was part of such discussions a lot of time, where, a scientist might ask only, okay, when will that thing be integrated? And the scientist does not care about SiLA 2. It does not care about how the file goes from A to B and how that's working, but, he wants to drive, or she wants to drive the workflow forward. Yeah. Then if you talk to the instrument vendor, they might tell you, okay, yeah, well, how should we implement it? Yes, we can do SiLA, but we can also do OPC. We can do whatever you want, kind of. If you then go to an actual developer and say like, okay, hey, we really have to implement that now. Typically, the developer will ask you, okay, where's the documentation? And sometimes it's just, because you don't speak the same language, because documentation is not documentation. Yeah, everyone has a different need. And that's why, I think within Roche, a couple of years even back, we started one thing which we now moved even also, similar to SiLA, to, I would say, the public. And this is a project what we call Universal Integration Knowledge Base, or in brief UIKB, which is kind of a community-based knowledge base that collects integration information in a structured or semi-structured format. And I want to briefly guide through what that is. And in essence, the idea is to separate not to separate, but the two key components of the UIKB project are, on the one hand, a rule book. And that sounds very stiff and thorough. It is actually not. The idea is it's more like a guideline, for a certain standard functionality set that a lot of devices have, from a, you might call that a method perspective or a functionality perspective. And there actually we kind of even looked into the SiLA standard, and I would say that is very, very close how SiLA also approaches that. And the other part is actually the content, what we say. So this is actually, how do you now, enable such a functionality for a specific instrument and for a specific method? To show you that as a kind of a real life example, a bit how that could look like. So imagine again, you have a liquid handler here. What would be documented in that rulebook or in that functionality set? These are, of course, examples. So we would say, okay, there's a method called start, meaning, kick off a certain process on the liquid handler. You could have a function kind of get status, and you could have also method log, something like that. Yeah, and you would document that in a functionality set and it's like, okay, hey, this is really, describe that, what do you mean by method start or get status or something like that. Now, the point is, this is not really code. This is just, a functionality functionality that the instrument, so that specific liquid handler provides. And then the actual wiki content would be, well, to get that started for a certain implementation and a certain instrument, well, you just have to put a file in the certain directory, and then the software of that instrument kind of pick it up and it starts the method. Yeah, just a dummy example. That might not be a real life example, but just to get you the idea across how that is working. And of course, it can also be a DLL or whatever. Now, you can play that along also with other, devices or sensors. It might be that a certain sensor, like your temperature sensor, doesn't have really a method that is called start. Yeah, and that's kind of fine. And as you can clearly see, also, well, this would also work for SiLA on SiLA 2. A SiLA 2 server you basically can describe in a similar fashion. Okay, so this hopefully I came across how that UIKB is kind of structured. And indeed, we built several prototypes of that wiki. It was first a static page, then we moved kind of to a what you see is what you get editor. Kind of see like, okay, you have a certain instrument and you have certain integrations to that you can kind of find it and even adapt information already with similar to Wikipedia. We gathered feedback and learned a lot, and also talked to a lot of instruments, vendors and providers who said like, hey, actually all the documentation you're looking for, we kind of have, but it's not really easily accessible, or, well, we were more than happy to put it also to your wiki, but can you provide us an API such that, our developers just, push a button and, it gets sucked in from any kind of Git repository or something like that. Plus, of course, also there, we want to build a community around it and say like, hey, this really works, this does not work, this is a good integration, this is, not working for me, to kind of really engage in the discussion and find the right experts who worked with a certain instrument and a certain integration. How that actually, kind of look like is here for a brief example. So on the leftest column, you would have, basically the functionality set, and all the functions that this instrument has. You will see is it supported or not in the second column, and then, looking at, okay, what would be the interface, and already having some hints and even some, code snippets if you want, or you would just link to, also PDF or other sources, how that integration actually could look like. Well, as said, it's really in the public domain right now. We try to push it, beyond Roche, because we clearly see, it's not only a Roche thing, it's really benefiting, the whole life science industry. And, we integrated that with Pistoia, and we think really that is kind of crucial that, a neutral body brings in, not only the Roche perspective, but several perspectives, to encourage also, more people to contribute, but also to consume that information. In the interest of time, basically I will stop soon. But if you need more information, happy that you reach out to me or also to John Conway, who can answer more questions and more detailed questions on that Pistoia project. Well, I stop here basically with that is being my last slide, but I want to come back to the provocative question, what has standardization ever done for us? And that is kind of a bit of a look back how the digitalization evolved for us in PRED, where you can clearly see also certain standards and certain standardizations kind of develop. Yeah, you see here genealogy, ontologies, but also things like barcodes, that at one point also things like that needed to really become a certain standard. So I would say standardization has helped the life science R&D space a lot, and I'm really much looking forward to it if we can also bring SiLA 2 as kind of a standard to solve those challenges that I also presented here in my talk in the future. And with that, thanks for having me and happy to answer one or two questions.